Today we take up a slightly different, detour from what we've been discussing all this while. Just to recall what we did in the previous lecture, we had completed our discussion of the properties of LSI systems, but specifically continuous time LSI systems. In fact, we had directly or indirectly focused on LSI systems that were on a continuous time signal and yielded a continuous time signal as an output, right? We had not, in fact, we talked of the properties of causality, of stability, right, and of memory. And this was specific to situations in which the input signal was on continuous time or also continuous space, actually. And where the output signal also was on continuous time or continuous space. I mean, the variable t could be a space variable or a time variable. You may interpret it either way, right? Now, what we are going to do today is to look at a slightly different kind of indexing variable or a slightly different kind of independent variable, both for the input and the output signal. We are going to look at discrete independent variables. All right? Now, by discrete independent variable systems, what we mean is that the independent variable assumes certain values, all right, where it could be possible to order them. But it is not true that if you take any two values, there is always a value in between. Let me take an example. Suppose I take the time axis. I choose 2 points in time. Let's call them T1 and T2. So far, in our interpretation of the time axis, we always agree that no matter what points T1 and T2 we choose, as long as T2 is strictly greater than T1, there is always some other point, say T0, which is strictly between T1 and T2. So there always exists a T0, so that the point T0 here is between T1 and T2. All right? So it really means that there is a continuity in the axis. So no matter what 2 points we choose on the axis, as long as they are distinct, there is always a point in between. And this happens no matter how small the separation between the points. That's what we mean by continuity of a variable. We have implicitly, in all the discussions so far, assumed the variables on which the signals are defined to be continuous in this sense. Whether we talk about time variables or space variables. Even in space, the same idea holds good. I have always assumed so far in my discussion that if I take 2 points in space, then no matter how close those points are, it is possible to find a point in between them, so to speak. Now, of course, when you talk about two-dimensional space, then the idea of in between has to be redefined. All right? Well, one way to interpret it is that if I take 2 points in two-dimensional space, and if I draw a circle with one of the points as a center, then there is always going to be a circle, a generalized circle, which encompasses the other point. And there will always be points interior to this circle. That's the way to interpret in between. right? So, if I'm talking about two-dimensional space, so if I take suppose I treat this whiteboard as the two-dimensional space of interest. If I choose 2 points like this, then I might draw a circle with one of the points as a center and passing through the other. This idea of a circle can be generalized to multiple dimensions. In 3 dimensions, it would be a sphere. In multiple dimensions, you would have a hyper, sphere or a corresponding higher dimensional version of the sphere. All right. So the idea is that there would always be points interior to the sphere. There would always be points interior to the sphere. Similarly, here in 1 dimension, that sphere or the circle boils down to just 2 points. If you take T1, T2, then you would draw. You have the point T2, and you would have the point here T2 minus T1 away, right? So you could generalize the idea in that sense. Of course, a more appropriate way to generalize might be to think of the line joining these two. So you can draw the sphere, and then within the sphere one can visualize a straight line joining these 2 points. And it might be more accurate then to say that a point will be in between these 2 points if it lies on this line segment. So if it lies somewhere on the segment here, for example, then we say it is in between those 2 points in the sense of multiple dimensions, right? So one can extend the idea of in between to multiple dimensions also. Well, I am making these ideas rigorous because we need to understand very clearly the distinction between continuous and discrete. Now, what is a discrete independent? Now, all this refers to a continuous independent variable, right? What is a discrete independent variable? A discrete independent variable is one where one cannot always guarantee the existence of such a point in between. In fact, one can go the other way. One can say it is possible to bring in an idea of succession, or it is possible to bring in an idea of nearest neighbor in a discrete independent variable, right? So for example, suppose I take the time axis. So all this discussion was pertaining to continuous variables. Now we take the discrete variable. So suppose I wish to define a discrete time variable, then one could identify points on the time axis like this. Now of course in time one has an ordering. So let me call this, without any loss of generality, I could call this point the 0th point, this point the 1th point, the 2th point, the 3rd point, and so on. And once I identify a 0 point, I can also identify a -1 point, a -2 point. And therefore there is an ordering on the points. And that means that for every point there is an immediate predecessor and an immediate successor. So the idea of predecessor and successor can be identified in 1 dimension. In multiple dimensions also one can have discretized variables. For example, one could discretize space. So one could have a 2-dimensional discrete space like this. So I could have a grid like this. So this is a grid. Now there, of course, there is no notion of immediate predecessor and immediate successor. But for every point, there is definitely the notion of a neighborhood. So every point has a neighborhood. A neighborhood is a set of points such that they are in some sense the nearest points to that point. For example, to this point, the neighborhood would be, say, this point, this point, this point, right? This point, this point, this point, this point, and this point. This would form a neighborhood, a 2-dimensional neighborhood of this point. So one can identify a neighborhood. Now this notion of neighborhood is absent in continuous variables. So this is a strict or a more precise formulation of what we mean when we say an independent variable is discrete, right? And just as one can define signals on a continuous variable, which appeals with our understanding of the natural world, because we do understand or perceive most of the independent variables in the natural world as continuous. We perceive space as continuous, we perceive time as continuous, right? So it helps to start our understanding of systems with continuous time independent variables, but it's important for us to generalize the notions that we have studied to discrete independent variables. So what do we mean by a signal defined on a discrete independent variable? It means for every such point that we have chosen in the space of the independent variable, whether it's a one-dimensional space like the time axis, so you have points in time, or it's a two-dimensional space, right, like the whiteboard which is being shown here, on which you have a grid. At every point so identified, or at every value of the discrete independent variable, a value of the signal is assigned. So corresponding to every point here, there is a value assigned to the signal. Alright? So in fact, you could think of it like a table, point versus value, point versus value, point versus value. Alright? Of course, you can also think of a similar table for continuous time systems. But there is, there is an infinity in between. Between any two entries, there is also a number of other entries. Right? Here, that's not the case. Here, in fact, it's interesting. I mean, I'm going to make this statement, perhaps it may not appeal to you immediately, but it happens to be true. What is a discrete independent variable? One where you can put the values of the independent variable in one-to-one correspondence with a set of integers. Now this holds not only for one-dimensional variables, but also for multi-dimensional variables. So that means even if I have a two-dimensional grid, I can still talk about point number 1, point number -1, point number 0, point number 2. So I can put the points in one-to-one correspondence to a set of integers. That's what we mean by a discrete independent variable, right? I shan't carry out the argument as, it's a little counterintuitive in the sense that it doesn't immediately appeal to our intuition to accept that even if I have two-dimensional grids, I can still put them in one-to-one correspondence with a set of one-dimensional integers, but that actually happens to be true. I'll leave it at that. So I think we understand the notion of a discrete independent variable. I would invite questions if there are any, if you have not understood, or if there are any doubts to be clarified. But now we'll agree that, we'll have a notation. So far, we've been using T as a generic notation for the continuous independent variable. Now we shall use N as a generic notation for the discrete independent variable. Now, one simple situation can be the following. You could choose the time axis and you could find uniformly spaced points on the time axis. So you could decide that I'll choose points on the time axis which are located 1 millisecond away and choose a starting point. So here is my time axis. Choose the starting point of sampling, I call it 0, right? Then I choose uniformly spaced points, say 1 millisecond away. Point number 1 is 1 millisecond away from 0. Point number 2 is 2 milliseconds away from 0, and so on. This is one simple way to create a discrete time axis from a continuous time axis. So it's called a uniformly sampled time axis, right? So we say uniformly sampled time. So what we'll do is, we shall illustrate most of our ideas pertaining to discrete independent variable systems by using this case, the uniformly sampled time axis case. And we will refer to this number as n then, this integer that we get as n. Yeah? So naturally, we shall have a system defined on this variable. Now there are various possibilities. You see, please remember, we have the input signal and the output signal. We can have 4 possibilities because each of them could be continuous or discrete. So we can have a continuous input independent variable and a continuous output independent variable. That's what we've been doing so far. We could have a discrete input independent variable and a discrete output independent variable. That's what we shall do now. But in principle, one can also have a continuous input variable but a discrete output variable, or a continuous output variable and a discrete input variable. And those cases have their importance. We shall see examples later. But right now we shall concentrate on the situation where the input variable is discrete Therefore, see, naturally, since the input variable is discrete, instead of talking about signals, we shall now use a different name. There is clearly a sequencing. There's clearly a sequencing of the variable values, right? You can talk about value 1. What is a sequence? A sequence is something which can be ordered according to the integers. So you can have a sequence of values. So we'll call it the input sequence instead of the input signal, right? So input sequence. And we shall, as has been our convention so far, we shall denote the input to emphasize the fact that the input is discrete. We shall use a square bracket instead of a round bracket. So wherever we have a discrete variable, we shall prefer to use a square bracket. We shall follow this notation. Discrete system, we'll call it a discrete system. A discrete system is one where the input and the output variables are discrete. And it shall produce an output sequence which also therefore is defined on a discrete variable. Y of n. All right? Now, before we start, building up properties of this, I must again emphasize that there are 2 other kinds of systems possible, which are mixtures of continuous and discrete systems, where instead of this, you could have this on a continuous independent variable or this on a continuous independent variable with the other being as it is. Right? I must emphasize this before we proceed. And they have their importance. We shall see examples later. Now you see, at this point in time, we should ask ourselves, see, suppose I am doing some analysis on a continuous time system and I come to certain conclusions, and I happen to discretize a time axis and try to carry out my analysis on the corresponding discretized time system. Is there some equivalence between them? Is there some relationship between them? This question arises in our minds right now. But we are not in a position to answer it right now. It will take us quite some time in the course to come to a stage where we can answer this question. In other words, can we relate continuous and discrete time systems? Or can we use a discrete time system to analyze a continuous time system? And so on. This question should be raised at this point in time. But the answer shall take us quite a while, and there is more than one answer, because there are many different ways of doing it, right? So we'll let this question germinate in our minds and, continue to play in the background. In any case, coming back to this situation. Now, you see, most of the notions that we have defined for continuous time systems can be extended in a straightforward manner to discrete time systems. For example, let's take the notion of memory. A discrete time system will be said to lack memory, or will be said to have a memoryless character if yn depends only on xn specifically. Yn depends only on xn. And not xm for m not equal to n. We will also be able to extend the notion of causality. So, a discrete time system is causal. It holds. Now, I will write it straight away in formal notation. For all. This is a symbol for all. x1, x2, such that x1n is equal to x2n. Now, I think this should be written in brackets. x1n is equal to x2n for all n less than equal to n0. The output y1n is equal to y2n for all n less than equal to n0. Corresponding outputs. And this holds, very good, yes indeed, this holds for all n naught. So all this holds for all n, yes. So in fact we should put a big bracket here, and this for all naught should apply to the whole argument. Very correct, Samir is quite right. Is it right? Yes, so this is, now this time actually we could have made this very formal definition in the context of in the context of continuous time systems as well. But I'm just restating the definition here for discrete time systems clearly. All right. Now, the ideas can be generalized similarly to stability. All right. So here, causality. What is? Well, I think we should also restate the idea of causality from a slightly different perspective. Right. What does causality mean? Causality means that the output does not occur, or the output does not change before the input changes. Or another way of saying it is, the system does not depend on future inputs to produce the output. Right. The system, so an informal way of saying it is, the system produces an output based only on past input samples. right? There is a notion of past and present because we have an ordering. Because we have an ordering, there is a notion of past and present. Yeah? Now, similarly, we can generalize the notion of invariance. So, what would shift invariance mean in discrete time? If xn produces yn, then xn 0 produces yn minus n0. And this holds for all n. So now I shall introduce the notation z. This script z denotes the set of integers. The script z is the set of integers. Yeah? Now please note that this is meaningful only for n naught, an integer here. And that's the difference with continuous time systems. There, any continuous shift is permitted. Here you can have only discrete shifts. Yeah? But for every possible discrete shift, one does have this shift invariance obeyed. That means if I shift the input by a discrete shift n0, n0 could be positive or negative. The output is also shifted by the same n0 and no other change takes place, right? One can generalize the notion of stability. Stability is so much easier to generalize because the idea of boundedness has very little to do with whether the variable is continuous or discrete. Yeah? So stability is very easy to generalize. So stability. Idea of bounded input, bounded output stability. So let's, state stability formally again. Actually I'm going through this exercise of stating them formally because now with our informal explanation of these properties in the context of continuous time systems, we can also endeavor to use the same formal definitions for the continuous time case, alright? So for every x such that there exists, now this is a symbol for there exists. For every x such that there exists a bound mx greater than or equal to 0 with mod xn less than or equal to mx for all n. So you must keep putting brackets. For every x, that means for every bounded input. So what are we saying here? I should summarize, in simple language, for every bounded input. What should we write? For every bounded input, the output is bounded. So how do we state that in mathematical language? There exists an my which is greater than or equal to 0 with mod yn less than equal to my for all n, but this is not complete. Of course, needless to say, here we are assuming that xn is the input and yn is the output. But this is not complete because we should emphasize that mx is less than infinity and my is also less than infinity. That should be clear. So in fact, we should perhaps correct this a bit, shouldn't we? We should say there exists an my which is greater than or equal to 0, which is strictly less than infinity. And we should also emphasize the same point here by saying this my is greater than or equal to 0, but strictly less than infinity. That's what we mean by, in fact, this is critical. Without this, the idea of boundedness is not captured. We must write strict here, strict, otherwise it has no meaning. So, formal statement of stability, bounded input, bounded output stability. Yeah. Now, it's good to get used to writing. This formal way of writing things helps because a lot of literature writes it this way. So, it's helpful to be aware of this formal way of writing things. Yes, Uday. Yes.
So, can you explain the ordering once again? So, how is the correspondence 1 to 1, and is it unique to the set of integers?
All right. Okay. The question is, why is there always a one-to-one correspondence between a set of integers and a discrete variable set? Well, actually, as I said, I wouldn't like to go into that aspect in this course, right? It's a little beyond the scope of, all right, let's see. I'll take up that point a little later. But let me take the case of the continuous time, so situation which has been discretized, right? So if I have a continuous time axis which has been discretized, if I've sampled it uniformly, so I've started at a point in time and I've taken points in time after that spaced uniformly from the first point, then clearly there's an ordering, right? Similarly, if, all right, let me example to illustrate. You see, yeah, let's take a multidimensional example. Since the point has been raised by Uday, let me take a multidimensional example to illustrate. Yeah. So what one can do is, suppose I start, suppose I'm sampling two-dimensional space, all right? Then I could start with some point in two-dimensional space, all right? And I would have a grid all around it, right? There would be a grid all around it, so to speak. It could be, it could be uniform, it could be, prefer it to be uniform, right? So let's take a situation where there's a uniform grid. Uniform grid means, you take a uniform spacing in the horizontal direction and a uniform spacing in the vertical direction. And I construct points like this, right? So it's a uniform grid. Now the question is, how can I order these points according to a set of integers, right? One very simple way to do it is as follows. You take any point as a center point. Let's take this as a center point. Right? Now, you could, in fact, why integers? Just the whole numbers, right? So you could call this point 0. Now you draw a circle with radius of 1 around the point. That will encompass these 4. A circle with radius of 1 will encompass these 4. All right? Then draw a circle with radius 2. So that will encompass the next set of points. So, 2 will encompass this. It will also encompass this, is it not? And so on. So, you can visualize it. You can draw a circle with radius 2. Now, you see, as you keep increasing the size of the circles, see, we'll say a point is in the circle if it falls either on the boundary or inside. So each point is clearly either in the circle or outside the circle. There's no problem, right? Now, also in each circle, right, you could order the points by going either clockwise or anti-clockwise, right? You could order the points by going either clockwise or anti-clockwise. So, you can start, and it doesn't matter which point you start from in the circle, right? So you could say, well, the center point is 0. Then in the first circle, you number the points 1, 2, 3, 4 in order until you finish all the points, and you number the next set of points. Say if you finished 4 points in the first circle, start from 5, right? So 5, 6, 7, 8, 9, and so on. So keep on ordering the points by proceeding either clockwise or anti-clockwise in each of the circles of expanding radius. That's one way to order the points according to a set of natural numbers, in fact. So one can work out a variant of this scheme for the set of integers. So, there could be, in fact, and there are so many possible orderings. I mean, one can always, so it is possible to put all these points in one-to-one correspondence with a set of integers. Yeah, just a moment. Yeah.
So since it is not unique, then what is the point? Because given just a sequence of integers, I cannot get back the points in the 2D plane. Since this mapping is not unique, I could have chosen any arbitrary rule to map it to the set of integers.
Well, let me ask you the same question for one dimension. See, we have in our mind one particular ordering for one dimension, but I could do the following. If I have some eccentric quality in me, I might decide to order the one-dimensional points like this. I could say 0 is here, 1 is here, then 2 is here, then 3 is here, then 4 is here. Alright? So in principle, the ordering of points is not sacred, although there is a natural ordering here. I agree, in one dimension, there is a natural ordering. In multiple dimensions, there is no natural ordering. There is nothing like a natural ordering. So to bring in, you have to decide on one ordering. But an ordering is possible, right? Of course, a particular ordering may be natural or unnatural depending on what you want out of it, right? A particular ordering could be natural or unnatural depending on what you want out of it. So you see, ordering in that sense is never unique. There is an infinite orderings, but very often there is one ordering that is preferred or not preferred, right, for a given situation. Is that all right? So in fact, I was not planning to take this issue up, but I think it's good we answered this question. So as you can see now, this also explains to you why I said that, when you have a discretized space, it's always possible to put it in one-to-one correspondence with a set of integers, right? In fact, if you wish, with a set of natural numbers, if you like, right? Anyway, coming back to the notions that we are talking about, so we were talking about stability, right? Now, stability is clear, bounded input, bounded output. So what does it mean in short? What are we saying when we say a discrete system is stable? We are saying if the input is bounded, the output is bounded. What do we mean by the input being bounded? If you look at the magnitude of the input samples. Now we are talking about input samples, right? Because at every point n, there is a sample, So if every input sample has a magnitude which is less than equal to some fixed mx, suppose non-negative mx, then there also exists such a bound my for the output, and this happens for every possible bounded input. Alright? Needless to say, I must emphasize that the test of stability only can be done when the input is bounded. If you give an unbounded input, nothing can be said about the output. Alright? It could happen that and just because the output is bounded, nothing can be said about the input. So it could happen that you have an unstable system where you see a bounded output in spite of an unbounded input, or in spite of, so all things are, it's only when you give it the test of stability is only when you give a bounded input to the system. This must be very, very clear. Unless you give a bounded input to a stable system, nothing can be said about the output. So if you give an unbounded input to a stable system, it could produce an unbounded output. I am just emphasizing this because it is a common error to assume that because you see. So we continue then with the discussion of the next property, namely linearity. Now, of course, again, I must emphasize that for discrete time systems, as for continuous time systems, the property of memory or memorylessness, the property of stability, the property of shift invariance, and the property of causality are all independent. So any of them can exist without the existence of the other. and any combination of them can exist, leaving out the rest. Yeah. Coming back to linearity. Now we'll again classify linearity into two parts, right? We did before. Additivity and homogeneity, or scaling. Right? We shall, as I said, intentionally look at these two properties separately, because there are systems that have one but not the other. What does the property of additivity mean? Additivity means the following. If the input x1n to the system produces the output y1n, and the input x2n to the system produces the output y2n, then the input x1n plus x2n to the system produces y1n plus y2n. So when you add the inputs, the outputs are also correspondingly added. Straightforward. What does homogeneity mean? Homogeneity tests only with one input and one output. Right? If the input xn to the system produces the output yn, then the input alpha times xn to the system would produce the output alpha times yn. For all constants alpha. Now, this is very, very important. For all. Now, both, when I write for all, I am talking about additivity and homogeneity. For all possible x1, x2, x alpha. That means for all possible x's which produce y's, and for all constants alpha, it's not enough to have it only for one constant. For all constants alpha, alpha times xn must produce alpha times yn. And similarly, for all possible inputs x1 and x2 which produce y1 and y2 respectively, x1 plus x2 must produce y1 plus y2. Right? So these are the properties of additivity and homogeneity. And as in the case of continuous time systems, if a discrete time system is both additive and homogeneous, it is linear. So linearity means additivity and homogeneity. Now, of course, I have already given you examples in the context of continuous time systems to illustrate, additivity but non-homogeneity and homogeneity but not additivity. A small variant of those systems would go through here. For example, a system that complex conjugates is additive but not homogeneous. A system that picks the maximum value, so to speak, is homogeneous but not additive. And I have also given you other examples of homogeneous but not additive systems. There is no fundamental change that is needed to carry that concept to the discrete time case. Right? So linearity goes through as it is. Now you see, there are a lot of things that carry very straightforward from the continuous time case to the discrete time case, we've seen a lot of the properties carry forth in a straightforward manner. Actually, so does the important notion of linear shift invariant systems. Right? So, a discrete time system is said to be linear and shift invariant if it is both linear and shift invariant. Right? So, we will concentrate our attention for some time now on linear shift invariant discrete time systems. Actually, I'm avoiding saying discrete time systems because, it's not necessarily time that is discretized. So, I'll just say discrete systems. Now, you see, I don't need to provide the same long preamble as we did for continuous time systems to explain to you that because we have focused our attention on the smaller class of LSI discrete systems, there is going to be something much easier that characterizes the system, namely the output to a specific input. So, in fact, we are going to now just add or make the small changes in the proof that we had for continuous time systems to show that for discrete systems also the impulse response is a complete characterization. But here we need to be a little careful. In fact, we don't need to be a little careful. Here, things are much easier for us. The idea of an impulse is far easier to define in discrete systems. Right? Let's see what the definition is. So, we will define a discrete sequence. The unit impulse discrete sequence is a sequence which we might denote by delta n in carrying over from the continuous time notation. So, that delta n is equal to 1 for n equal to 0 and 0 else. Very beautiful, because there is no difference between sequences and this particular sequence. This is also a sequence as much as any other. This is in contrast to the unit impulse in continuous time, where we had to be very careful and say, well, the unit impulse in continuous time is not a function. It's a mathematical object which behaves in a certain way under integration and so on and so forth. The unit sequence is a respectable sequence like any other sequence, right? It's well defined. You can do anything that you do to other sequences very well onto the unit sequence as well, unit impulse sequence as well. And just as we can define a unit impulse sequence, we can also define a unit step sequence, right? A unit step sequence defined un is a sequence that is 1 for n greater than equal to 0 and 0 for n less than 0. Again, so much neater, because there is nothing like a discontinuity here. Either you say the whole thing is discontinuous because it's a sequence, or you say the whole thing is continuous because it's well defined everywhere. Right? So, in fact, in some sense you can see that discrete time systems actually become easier to handle. In some ways, discrete time systems are easier to handle. So, some people like to start by considering discrete time systems or discrete systems and generalize to continuous systems. But I think there are some places when one takes that kind of an approach, there are some places where one runs into trouble. So, I prefer to stick to what I have been doing so far. Now, you see, any sequence xn can be written as a linear combination of unit impulses. We will see how. Let us take the following sequence xn. Let us take, to illustrate the idea, let us consider a sequence xn which has compact support. We've defined the idea of compact support earlier. Here, when we talk about compactly supported sequences, we mean sequences xn where there are only a finite number of non-zero samples. So let's say, for example, the non-zero samples of xn lie between -2 and +2. All other samples are 0. So the sample value at, this is one way. I'm just showing you also another way in which sequences are often denoted. So at -2, the sequence takes the value, let's say 3. At 1, it takes the value 1. At -1, it takes the value 1. At 0, it takes the value -3. At 1, it takes the value 2. And at 2, it takes the value 5. Let's say, just for the sake of example. This is one way to draw a sequence. Of course, one must remember here, these were all real values. They could be complex values as well. In which case, you should visualize a two-dimensional plane passing through each of these points and draw the line in that two-dimensional plane. Yeah? Now, this sequence, of course it is, you assume it is 0 else, here and here, so it's 0 everywhere else. Now this sequence can be considered as a sum of many sequences, in fact precisely a sum of 5 sequences. A sequence which is 3 at -2 and 0 everywhere else. Sequence number -2, I'll call it sequence number -2. Sequence number -1, which is 1 at -1 and 0 elsewhere. Sequence number 0, which is -3 at 0 and 0 else. Sequence number 1, similarly 2 at 1 and 0 else, and sequence number 2, which is 5 at 2 and 0 else. Alright? So I might write this down. So you see now, what is a sequence which is 3 at -2 and 0 else? It could be thought of as a multiple of a unit impulse sequence shifted so as to lie at -2. So consider delta n plus 2. Delta n plus 2 is the unit impulse sequence shifted to -2. Right? Delta n plus 2. Delta n plus 2 is equal to 1 when n plus 2 is equal to 0, because n is equal to -2 and 0 everywhere else. So 3 times delta n plus 2 will give you this point, plus 1 times delta n plus 1 shall give you this point. Alright? And similarly the others. Now what are these numbers 1, 3 and so on? They are the values of the original sequence at this point. So what is the statement we are making in total? What is the statement that we are making in total? The statement we are making in total is that xn is summation over all k, the value of x at the point k times an impulse located at k. Delta n minus k is an impulse located at k, right? And delta n minus k times xk gives you that particular sample of x at the point k. And when added over all the samples k, it gives you the sequence xn. Right? What is the statement that we have made here? Any input x, any sequence xn is a linear combination of an infinite set of shifted and scaled unit impulse sequences. Alright? Now we shall in the next lecture make use of this definition to construct the output of a discrete LSI system. Right? So we conclude the lecture here today and proceed from here the next time.